Hi, my name is Miguel. I'm a master's student in physics in the University of Coimbra in Portugal. This is my final presentation for Seminars 1. It's titled Quantum Computing with a Single Qubit from Quantum Mechanics to Quantum Variational Algorithms. Now, I've split this presentation into 3 parts. The first part is called Quantum Mechanics from Scratch, and that's because we're going to be deriving some important principles from first principles. Then I'll be talking about classical computing and quantum computing and how they relate to each other and some important aspects of both. And then finally, I'll be talking about some very exciting recent results published by the University of Barcelona by the QUANTIC group, where they have shown that even a single unit of processing power in quantum computing can be used to perform non-trivial computations. But we'll talk more about that when we get there. So let's start with quantum mechanics. Now, it has a bad reputation, especially in pop culture. Quantum mechanics is used all the time as this incomprehensible thing to explain away other incomprehensible things. But not everybody thinks that it needs to be very complicated. This is Scott Aronson. He's a proeminent quantum computing expert, and he argues in his book Quantum Computing Since Democritus that you can derive some pretty important and maybe not obvious at first sight results starting just from thought experiments, and that's what I'll be doing with you now. So this is a coin, and in particular, it's a fair coin. And what that means is that the probability of each outcome of the coin, it has 2 outcomes, heads and tails, is equal to 1/2, or 50 out of 100. We know how to generalize this concept of probability to more outcomes, as long as the probabilities we consider for each outcome add up to 100%. The reason for this is obvious. It's that if you're going to observe an outcome, you are for sure going to observe some outcome. Therefore, the total probability of something happening must be 100%. Now, what if for some reason we were interested in including negative numbers in the concept of probability? We can't really change the concept of probability itself because it's such an intuitive notion that if something has a probability of, for example, 1/9, that means you'll observe that outcome on average 1 out of 9 trials. But there is a way to include negative numbers in this whole deal. And that way is to consider not the number we're talking about, but rather the square of the number. So your condition for a set of numbers being able to describe a number of outcomes is now not that their sum is equals to 1, but rather that the sum of their squares equals 1. So we need to make a distinction. The number itself is the probability amplitude and can be positive or negative. So you'd have a probability amplitude of -1/3, say. And the probability associated to it, you get that by squaring the number. And that's still probability as we know it. So a probability amplitude of -1/3 would have an associated probability of 1/9. So some outcome with a probability amplitude of -1/3 will occur on average 1 out of 9 times. If we consider again a two outcome situation, so essentially a coin, but with probability amplitudes rather than probability, you'd have 2 probability amplitudes naturally, and I've designated those here by A and B, and because of what I've just said, A squared plus B squared would equal 1. You could represent this as a right angle triangle if you remember Pythagoras' theorem, which is why Pythagoras' face is on the coin. Now consider 2 coins which obey probability amplitudes, and these are similar coins, except that the right-hand side coin has a probability amplitude of tails of not square root of 50%, but of minus square root of 50%. Now, squaring any of these probability amplitudes, you get a probability of 50% for both heads and tails for both coins. So if you were given 2 coins, the coin labeled number 1 having both probability amplitudes positive, and coin labeled number 2 having the probability amplitude of tails negative, and you tried flipping them to try and distinguish them, essentially, what you would get is something essentially indistinguishable. You'd get heads half the time and tails half of the time on average. So if we notate it like this, and these are the probability amplitudes for both of the coins I've just said, the question arises whether there is any actual tangible difference between considering probability amplitudes or not. This is to say that if I can't distinguish coins 1 and 2, then the notion of probability amplitude is completely artificial. Well, to show you that yes, we can in fact distinguish these two coins, we need to first talk about a machine. This machine is labeled H, and what it's going to do is it's going to take in a coin which obeys probability amplitudes and return a new coin which obeys different probability amplitudes. However, these new probability amplitudes are calculated from the old ones using a fixed formula. In particular, what we have is square root of 50% times the amplitude of heads plus square root of 50% times the amplitude of tails as the new probability amplitude for heads, and then something very similar but with a minus sign for tails. Now, you could represent this like this if you were interested in actually doing the math, but here's quite simple, so we can just stick to the previous slide. If you were to feed it the first coin, that is the coin that has positive probability amplitudes, what you would get by doing the math is something that has a probability amplitude of 1 for heads and probability amplitude of 0 for tails. So if you square those, you still get 1 and 0, which means that this new coin, this coin that H produces when it's fed coin number 1, is completely biased towards heads. You flip the new coin, you always get heads. However, if you were to feed it the second coin, and the second coin is the one whose tails has a negative amplitude, what you would get would be something not completely biased towards heads, but rather completely biased towards tails. And this is a very important conclusion because it tells us that although coins number 1 and 2 may not be immediately distinguishable, we do have a procedure to distinguish them. And this does tell us that probability amplitudes are something different from just considering probability. But we can take it even further. So we could visualize our first coin, the one with both probability amplitudes positive, as a right angle rectangle, as I've said. And if the black segment represents the amplitude of heads and the orange segment represents the amplitude of tails, then because the other coin has a negative amplitude for tails, we could represent this like that. So that's still a right angle rectangle, so it's still fair game, but now it's pointing the other way, and we could associate that with a minus sign. What if, however, this other segment was at an angle? It's still a right angle rectangle, and the hypotenuse still measures 1, but it should represent a different coin if we're following this reasoning. In fact, there is a way to represent that sort of offset, and the way to do that is using complex numbers. If this segment, so we take our blue segment as a reference, and if this new segment, this pink segment, is at an angle phi with the blue segment, we can represent that mathematically by a factor of e to the I phi on the probability amplitude of tails. And that forces us to make a slight change in the requirement that the squares add up to 1, and say rather that the squares of the modulus of the probability amplitudes must add up to 1. This is simply because of a quirk on how squaring complex numbers work. And let's formalize this a little bit. Our state is our coin, and it's described by the probability amplitude of an outcome times the state associated with that outcome. So we have two outcomes, those are heads and tails, and we have two probability amplitudes multiplying by each of the outcomes. So our state could be, so if you were talking formally about this, your state would be psi, and then you'd have two outcome states, which would be 0 and 1, a probability amplitude associated to outcome 0 of A, and a probability amplitude associated to outcome 1 of B times e to the I phi. It is this that we consider a qubit. It is a state like this. It is a probability amplitude distribution with two possible outcomes. We can take this even slightly further, and we'll see why this is useful ahead. and rewrite A and B as the cosine and sine of some angle theta over 2. And the reason why this is useful is because we can now have a visual representation of a qubit by using angles theta and phi. This is called a Bloch sphere. To see, for example, so an example of representation of our Bloch sphere, in our Bloch sphere, we have the two coins we previously discussed, and both of them are at the equator, so they'll have a probability of 50% of both heads and tails, but they are at different points of the Bloch sphere, so they have different probability amplitudes. Okay, on to computing. Now, in a science context, when we talk about computing, we're not talking about personal computers or anything you might associate typically with a computer. What we're talking about is some sort of machine, even if imagined, that takes in some input, performs some operation on that input, and outputs some predictably output. So it's maybe more akin to a calculator. This sort of computation may be anything from an arithmetic operation like addition, subtraction, division, to something like data classification, function evaluation, and so on. And the way to formally define a computer in these terms is to first talk about these atomic machines. What I mean by atomic machine is these machines that classically will take in a bit that is either a 0 or a 1 and will produce a new bit, new output for the bit you're given. And you need to know all outputs for every possible given input. So if the input is of a single bit, that is, if the machine only receives a 0 or a 1, then the only thing it can do is flip the 0 to a 1 and the 1 to a 0. But your machine may take in more than one bit and may produce output depending on the whole set of the bits. You then chain these machines, these atomic machines, whose formal name is gates, into what we call a circuit. So you have these wires, which are these lines carrying bits. We're still talking classically, remember. And then each of these gates will act on one or more wires, depending on whether the gate takes in one or more bits, and will change these bits on the wires depending on what it receives. By the end of the circuit on the right-hand side, you'll have your output. So essentially a circuit on the left-hand side has some input, it processes that input and produces some output on the right-hand side. And there's two ways to measure how complex a circuit is. The first measurement is how many slices, in a sense, so number of gates you need on your computer. Now, the idea here is that a gate takes a fixed amount of time to process whatever input it's given. So if you need, for example, 3 slices, that is no more than 3 gates acting in serial, you'll have your circuit will take 3 units of time to process whatever input it is given, because you're assuming also that if 2 gates are acting in parallel, they'll be performing the work at the same time. And it is for this reason that this is called a time complexity measure. On the other hand, you also need to know how much memory, how many wires or bits your computer needs to both phrase the input and the output. And that is why you could also have a memory complexity measurement. And what does any of this have to do with quantum computing? Well, recall that we've talked about this machine H, and what it is doing is not too dissimilar to these gates we've just talked about. But rather than taking in a bit that is either a 0 or a 1, what it's doing, it is taking a qubit, a quantum state, and producing a new, also valid quantum state, depending on what it was given. In fact, this is a gate. It is a quantum gate for exactly these reasons, and it is a very important gate in quantum computing. It is called the Hadamard gate, and it is defined as we see here on the screen. Now, because we know the linear algebra description of the gate, because we know the matrix form of the gate, then we know how to compute for every possible input, every possible output. So this is one of those atomic gates I was talking about. But again, it is not acting on bits, it is acting on quantum states. Therefore, it is a quantum gate. You could define many such quantum gates. Here you have some very important ones. From top to bottom, that's a Hadamard gate, a NOT gate, a T, and a T-dagger gate. And on the right-hand side, you have their definitions. So you know what they'll do to any given input state. So you, very similarly to what you would do classically, you can chain these gates on wires which carry now not bits, but rather quantum states, and use the cumulative action to perform some sort of computation, where your final state, your output quantum state, will codify your answer. But this can get very unwieldy very fast. And in fact, it turns out that quantum computers are not great at doing the same things as classical computers do. This circuit you see here, what it's doing is it's comparing two numbers and deciding whether the second number is greater than the first one. So we actually need a way to reason about the action of these gates and to construct new algorithms. And this is why the Bloch sphere is so important. It's because the Bloch sphere actually allows you to reason about the action of one gate on a single qubit. For example, the Hadamard gate, what it does is take your point on the Bloch sphere and rotate it 90 degrees around the y-axis. And the T-gate, another one of those gates that I've shown recently, takes your input point on the Bloch sphere and rotates it 45 degrees positively around the z-axis. But if I'm saying that any gate of a single qubit simply performs some sort of rotation, that we don't really need to consider each one of these gates in separate. We can instead just think of these three rotation gates, one that performs a rotation around the x-axis, one around the y, and one around the z-axis. And the reason for that is that if any gate is essentially a rotation, then using these three rotation gates, we can compose any of the other operations. Now, remember that for classical computing, I said that if a gate only took a single bit, there was only one possible thing we could do, and that was to flip the bit. But that's not the case here. We have a whole surface to work on now. There are many rotations I can perform on this sphere. And this may lead us to ask, can we use a single qubit to perform some computation? Now, the group at the University of Barcelona, the QUANTIC group, have answered this question. They have said, yes, you can use a single qubit and perform some computation. In particular, what they have done, and I'm going to skip a slide here for a second, is they've classified data. So you give it some data like elephant, and then you try and you ask the qubit to put it in a category, for example, mammal. But it's not as simple as it might sound, because, as they say, a single rotation cannot capture any non-trivial separation of patterns in the original data. What does this mean? Well, it means that if you only get to perform a single rotation, if you have your input point, and you know what rotation you're doing and by how many angles and around what axis and etc., then that's essentially the same as saying you already know what the output is. Because, performing a rotation on the input, well, you know your rotation, you know anything there is to know about it. So if the rotation is completely defined, what computation can the qubit perform? What can the qubit tell you that you don't already know? So the only way to have a single rotation would be to already put all of the information in the rotation. So you're essentially getting nothing out of your computer. Okay, so their approach was slightly different. Since their approach was to perform a classification, and so they took inspiration from a classical technique that has been very good at doing exactly that, at classifying data, and that is neural networks. Now, neural networks, if you're not familiarized with them, act on a principle that you feed it classical data, so it's a wholly classical process, but you feed it some input data, and that's those two balls at the left, and you feed it to all of these named neurons, the squares. And each neuron is going to act separately and in a different way on the input data it's given. Then you could have a not pictured but second layer of neurons, and each neuron would receive the data from each neuron of the previous layer and act differently upon what it received. And then at the end, you smush all of this information into a single value again, or more than one, depending on how many values of output you want. But you smush all of the neurons' information into each of the output values. And this output value could represent, for example, a classification. Say that the output value was 1. Well, imagine you were interested in classifying as mammal or not mammal. 1 could mean mammal, and 0 could mean not a mammal. And 0.3 would mean, hey, I'm pretty sure this is not a mammal, but I'm not completely sure it's not a mammal. However, there's a problem. You can't just take the neural network technique and make it completely quantum, or say, okay, I'm going to do exactly what we do with neural networks, but do it with quantum states. And the reason for that is that you cannot clone a quantum state. So you cannot take, in the coin analogy, some coin and pass it into a machine that produces two identical coins like the first one. The reason for that is beyond maybe the scope of this presentation, but there is a very nice video by Minute Physics that will take you through it with little to no math. And why is this the problem? Well, because the whole thing is passing your data to each of the neurons separately. So if I'm passing the data from that circle over there to the first neuron, then there's no way for me to pass it again to the second neuron, because even though we might not think about it like that, what we need to do is actually clone the data, send one of the copies over to the first neuron and the other copy over to the second neuron. So what was their technique? Well, the input data will always be classical. Let's say we're trying again to classify whether an elephant is a mammal or not. We know how to represent, so you could have, for example, an elephant as a picture of an elephant. And you know how to represent that as classical data because, for classical computers, which we already have, we know how to describe images as a bunch of zeros and ones. And classical data can be copied, and we do that all the time. So why not copy it beforehand and then pass each of the copies into the quantum neurons? That's what's pictured here. Each of the neurons will be a quantum gate, as we've discussed, and a quantum gate acting on a single qubit, also as we've discussed, can only be a rotation. So to put it all together, what we'll have is a rotation that will depend on the classical data that we've pre-cloned and are feeding into each of the rotations separately. And more specifically, this rotation will be parameterized by two things. First, a theta angle, which is just some independent rotation, and then some omega vector, which will produce also a rotation, but is affected by the classical data that is fed to it. So you can see that by u being a function of theta plus omega, and that is a Hadamard product with the data. X is the data. And the trick is that each of the neurons, like in the neural network scheme, will convolute with the data in a different way. So both the independent rotation each of the neurons is performing, as well as the way that the rotation is intertwined with the data is different, which is why we index our thetas and omegas. So I've just made some visualization of the procedure. So you would have your quantum bit start in a position and then be taken about by each of the neurons. And by doing this, what we've done essentially is offload all of the computational work into these angles. So if you knew what these angles were, you would be able to classify any data, but we need to find what they are exactly. And the way to do that is again borrowed from neural networks. What we do is we train the neural network. What does training the neural network mean? Well, it means we take a bunch of data that we know both the input and the output. So you would take, for example, elephant, mammal, shark, not a mammal, and so on, and then feed the input into the machine with some, say, random angles set into it. So you would configure your quantum computing machine with random angles and that circuit we've just discussed, and feed into it elephant. And then you'd see if the machine successfully predicts whether the elephant is a mammal or not. So you compare the output with the expected output. Now, if it's not the expected output, what you do is you readjust these angles and you repeat this procedure until you have angles you are satisfied with. So until you have angles that successfully produce the correct outputs. And once you've achieved this stage, you may be fairly confident, if you have a good training data set, that for new inputs, the output will also be correct. This process is called a variational algorithm, precisely because what you're doing is you're varying your parameters slightly in order to try and optimize the results that you get. Because we're talking about quantum circuits and quantum algorithms, we have a quantum variational algorithm, and quantum variational algorithms have been very important for the state of the art because they leverage essentially the best of both worlds. You can perform some computation in a quantum context, and then optimization of the parameters, which is something we know how to do fairly well classically, can be offloaded onto a classical computer. We then feed the new parameters into the quantum computer and repeat the process. So this is why it's called the quantum variational algorithm. You need, so what is this? Now, you need a way to objectively quantify how good a given output is. So you might say, okay, say that I give it elephant and it says, hey, I'm 90% sure that it is a mammal. Our intuition tells us that that is 90% good because you are expecting 100% exactly prediction of being a mammal. But it's not so simple when we're using a single qubit to perform these classifications. Why? Well, essentially because you only have so much space on the Bloch sphere. So even if you have anything more than 2 points, even if it's close to the intended class, so the point associated with the intended class, it will still be close to some other points. And so what they've done in the paper is they first said, okay, our measure of goodness will be just how close it is to the intended class or to the intended point. But then they've said, oh, wait a minute, if we have a lot of classes, it'll still be close to other classes. So what they do instead is say, and that's what you have below on the second line, is your measure of goodness will be being close to the intended point, but also being as far away as possible. So you can, in theory, see how far away it can be from the other points. So it needs to be both close to the point where it should be and also as far away as possible from the points where it shouldn't be. And using these, we can now see results because although this is a theory, this is interesting only if we can perform classifications in practice. And yes, we can see that they do, in fact, make some very good predictions. Here is the first case they give, arguably simple. And the first thing they note is with just one layer, as they've said, a single rotation cannot capture any non-trivial separation of data. So with just one layer, the only thing you have access to is one rotation. And this rotation can't really separate anything. So no matter how much you train those angles you have access to, you're not going to be able to achieve any sort of useful classification. But the more layers you add, the more nonlinearities you have on the processing of your quantum state. And so the better classification you can achieve. And you can see here that by the point you have 8 layers or 8 rotations of the qubit based on different parameters, you have a pretty good separation of data. So they could successfully separate points within the circle and outside the circle. And they said, okay, so let's take it a step further and now have something a bit more complicated to classify. So they're going to try and classify into more than one class or 2 classes. So instead of just saying inside or outside the circle, we're now going to try and say which circle does it belong to or does it not belong to a circle at all. And again, what they argue at the beginning of the paper seems to hold. For one layer, you get essentially no non-trivial separation. But with 10 layers, you get very good separation of the data. And this goes on. So here is what they've called the annulus problem. And by the point, again, you have 10 layers, you have a very good separation of the points. So you have very good classification of the points as being inside the ring, in the ring, or outside the ring. And so in the words of the paper, a single qubit provides sufficient computational capabilities to construct a universal quantum classifier, and this fact may be surprising. Why is it surprising? Well, because as I've shown, quantum computing borrows a lot of the theoretical paraphernalia of classical computing, but it is fundamentally different. Whereas in classical computing, you can't really use a single bit to do anything. In quantum computing, you have this whole space to work with, and so you can actually do things. Let's see what the takeaways of this are. First, I hope you're now convinced that talking about quantum computing is more than talking about whether the cat is dead and alive. Because you could say, essentially, you could say that you have a probabilistic cat that 50% of the time is alive and 50% of the time it's dead. And much like a coin can be fair and be 50-50, once you observe some outcome, that is the outcome you've observed. So once you see the cat is either alive or dead. That's not the point. The point is that you have probability amplitudes. So you could have two cats that are both alive and dead, so alive and dead with 50% probability each, but they are not the same intrinsically. And that's what's important. And also, just how different quantum computing can be from classical computing, and just how amazing it is that a single qubit can be used to do things that are just simply non-trivial, to classify data. I hope that really drives home how different classical computing and quantum computing can be. And essentially, that's it. I hope this helped you understand a little bit more about what quantum algorithms are, what quantum computing is, what quantum computing isn't, and what quantum mechanics definitely isn't. And I hope this makes you as excited for the future of quantum computing as it has me excited.